Bismillahirrahmanirrahim. Yes, hello. Hi everyone. So we are taking the part 2 of source models of chapter number 4, and we are going to cover the flow of the source models for flow of gas or vapors into a hole in a tank or a hole into a pipe. So the first thing that we want to cover here, we want to mention is like we have, like for example, this is a storage tank and we have a hole here, and because this, like you have a gas within a tank, like it's pressurized, that's the usual case, and we have pressurized gas. So when this opens, we have gas going out really fast, right? Shooting out. So this gas which is going out, how much we are going to lose gas in this case? And in this case, we are talking about really here that the pressurized gas is really high, and now we want to calculate how much you're having of this gas leaving the system. So for flowing gases and vapors, these assumptions are valid only for small pressure changes and low velocities. That means what you are trying to calculate here, there are differences in pressures, double the pressure, but if it's greater than that, it could be more difficult to work on it. So what happens is the energy of that pressurized within the gas as a result of this pressure is converted into kinetic energy. As it opens, it just goes out, escapes, and goes through that hole, right? And of course, knowing the density, pressure, and the temperature of the gas will give us about an amount of the vapor that will exit that leak. We need to consider that when it discharges or leaves, right? It leaves through that hole. It goes either through throttling or free expansion releases. Throttling means what? Means there's a small crack, okay? There's a small crack within the system. And a small crack, that means there's a lot of friction losses, okay? Friction losses, because a small crack, there's no place. It needs to go and friction. There's a lot of friction and it needs to go through that small hole and pushing its way out, right? So but if you're talking about free expansion where there's a big hole, considerably big hole, I mean, most of the pressure energy that it goes out as a kinetic energy, and in this case you're going to consider it as an expansion, like this expansion release going from a small volume to a much bigger volume, and we consider this as an isentropic behavior. And in isentropic behavior, we already have the equations for isentropic behavior, so that we can find the relationship for P naught and the relationship for rho naught, or for rho, right? And we are going to see like how does the pressure change if there's an expansion, how does rho change if there's an expansion. It depends on what? It depends on the heat capacities in the liquid and the vapor phase, in which we name this as gamma, which is Cp over Cv. Okay, so source model for throttling is a bit tough, so we're not going to cover that. We're going to cover the free expansion release part. And in this case, we just start with our mechanical energy balance equation. That's our usually balanced equation. And what do we say usually? There's no change in the elevation, there's no shaft work, so we are left with this equation here. Okay, we are left with this equation here. Now this is not incompressible fluid, so we cannot say that this is equal to delta P over rho. So that is not possible. And here actually the pressure, we are going to use the isentropic equation, the expansion equations, so that we can find the dP term here. Okay, and of course F is through friction losses, the same story that we went through, and we have an equation for the velocity, so that we have an equation for the velocity that will be substituted. So in this case, no shaft work, delta Z is equal to 0. This is incomparable to that, is 0, and we have a certain pressure and temperature at this pressurized place, where it flows or escapes here, it escapes out to the atmosphere. So this is like a free expansion gas leak, okay? They call it the free expansion gas leak. So this is the equation that we have here, and what we need to do, we need to take the integration to get this dP out term. We cannot just say delta P. Okay, and when we take a dp and integration, of course we are going to say that a dp from a certain p naught term to a p value. Okay, so it changes from p naught term to a p value. Doing this now, is it an ideal gas or not? We are going to consider that for simplicity as an ideal gas, just to get the trend that we are expecting. And as I said, because it's an isotropic expansion, we could use the generic form that we have from thermodynamics, and we can get the Cp and Cv values to calculate gamma. Okay, and again we have this alpha and C1. The C1 and alpha, we are going to deal with them as C naught, identical to what we have done before. So we substitute the equation for the velocity, and substituting the equation for the velocity, substituting equations for the expansion for the P over P naught. And after the substitution here, we substitute this U in that Qm term, and we are going to get our equation. Actually, our equation had a density term, so again we are going to substitute for the expansion, isotropic expansion for density. We are going to get this equation here. So this is the equation that I have, this beautiful equation that I have, which represents how the mass flow rate is changing. But for safety studies, we want to say that, well, I don't want to consider friction and so on. I want to consider the maximum flow rate of vapor through the hole. I just want to take the worst scenario, right? If there is an exit here, I want to go to the maximum. And the maximum here, how to calculate this maximum, which is about, we call it sonic. What is this maximum? We can calculate this maximum, which is P, right? We have a certain P naught to a certain P value. What is this maximum that I can get out here? The maximum that I can get if I derive this term, so I'm going to differentiate the above equation with respect to P over P naught. And then I will equate it to 0. And after I equal to the 0, which means that if I have something that is like that, I'm going to take the slope over 0, that means the maximum value. And when I calculate the maximum value, I found out that the P chalked, or the P max, or the P sonic, or the P critical value, or the P max, whatever you call it, right? So this is the P max or the P chalk value in response to what was the initial pressure. It depends on this equation here. So that is depending on what? That depends on a maximum pressure, right? So what is the choke pressure? It is the maximum downstream pressure resulting in maximum flow through the whole pipe for safety reasons, maximum. For downstream pressures less than P choked, the following steps are valid. The velocity of the fluid at the throat of the leak is the velocity of the sound at the prevailing conditions. It's like maximum, right? And the velocity and mass flow rate cannot be increased further by reducing the downstream pressure. We cannot expect an increase over a maximum. It's a maximum. This type of flow is called what? Choked critical. So that I'm just saying that it is called maximum. Okay, so P is equal to P choked. Okay, the maximum P that I'm going to have here. And actually, based on this equation that had been obtained when I made the derivation of P pi P naught equal to 0 and found the maximum P pressure, someone came and said that, well, I have made some of my studies, and through my studies, I saw that if I have a monotonic gas, only one type of gas, my gamma was 1.67, and I found out that P maximum is 0.487 P naught. And my diatomic and air, if it was diatomic, two types of gas, I have that gamma is 1.4, triatomic is 1.32, which is equal to 0.542 P naught. Okay, so it gives me a generic term of the P max. But by the way, right? What I really need is that maximum flow equation. This is what I need. Okay, this is what I need to do my calculations. I may use these if I have an idea that if it's monotonic, I can have an idea of the gamma, and I can have an idea of the P chalked. Okay, I can have an idea. Otherwise, all what I need here is just the P naught value, right? And I need the gamma value. And actually, if I cannot get the gamma value from here, I can get the gamma value. I can get the gamma value from here. Okay, so these are the gamma values, which is P over CV, for what? For all kinds of gases that could be released or could be escaping from that tank. So it could be a tank of ammonia. So I can calculate what is the gamma of that, and then I'm going to substitute my gamma here to calculate what? To calculate my QM chalked. However, if I have a tank of an air leak to atmosphere, so it's a tank of air, my P chalk is equal to 14.7, so it will be a different answer, right? But talking about the other tanks, I have the values of gamma. Even for air, I have the value of gamma. It's 1.4, right? So I have it here. I have it. And what about the C naught value? Okay, so here I'm talking about, I know the value of gamma. Okay, I know molecular rate R T naught. I know the universal constant, the temperature, the pressure, the area of the tank. I don't know the value of C naught. C naught is very similar to the one for the liquid. So if it is sharp edge, it's 0.61. And to talk about chalked flows, the maximum flow, then I'm going to consider that there's no friction. So C naught is equal to 1. And I cut it off there. Well, that was for flow of the gas or vapor through a tank. However, through a pipe will not be covered in this chapter, as we have mentioned earlier, and it's not part of the course syllabus. The next part is the flashing liquid. The flashing liquid, in which it's like having a spray. So this spray or the flashing liquid, this liquid goes to droplets, and those droplets are called aerosols, right? They are called aerosols. And they flow out here and there, right? These aerosols here and there. It's like any spray. It's like you're spraying a perfume, and you can smell, even though you can see the small droplets in air, but they just, of course, through alcohol substance, it just vaporizes really fast because of the vapor pressure, and you can smell it. Of course, it gets into your nose. So if you're talking about if the tank pipe or other contaminant device has a leak, the liquid will partially flash into vapor. That's what you're talking. We are talking about the liquid could become little vapor, and that liquid, which is toxic, could be very explosive. Okay, so again, what is a flash? It looks something like that, and since a flash is so rapid that the process is assumed to be adiabatic. Okay, adiabatic. And all the excess energy contained in the superheated vaporized liquid and lowers the temperature at the new boiling point, which means when it splashes, it goes to a new boiling point, and that's why it goes into a vapor phase. How to calculate the heat? So this is the heat. This is not the Q, right? This is not the flow rate. Here you are talking about the Q, which is MCP delta T. And the delta T I have here is between the T naught, which is the temperature of the liquid, and this is the boiling temperature, the depressurized boiling temperature. And what is the energy that will be released? This will be the energy released based on the difference between the depressurized boiling temperature and the liquid before depressurization, the temperature of the liquid before depressurization. And we know that Q is equal to mV over m, is equal to m into delta heat vaporization, and we also know that Q is equal to MCP delta T. And actually, by dividing these two terms, I will get mV over m is equal to Cp T naught minus Tb divided by delta HV. And this mV over V, it tells me the amount of vapor that will be, or the fraction of the liquid that will be vaporizing. Okay, so it will give me the fraction that will be vaporized. Actually, we also know that, well, what happens here is when you have a tank and you have vapors going out, the mass inside this tank is running out. And actually, there's a change in the mass here, okay? There's a change in the mass. And because there's a change in the mass, which also should be considered, so this is the dm term here. And if you go on and take the integration of both sides, and do the division, you're going to get the amount of the fraction of the liquid vaporized. Okay, so solving, you're going to get the amount of friction, the fraction of the liquid vaporized, which is FV. So what do we need to remember here? Flashing liquids escape through holes and pipes. Required some special consideration because two-phase flow conditions may be present. So we cannot really calculate exactly what is the flow rate here, but we will know how much vapor had been really going out. If the fluid path of the length is short through a hole, then we are going to consider some consideration here. If the fluid flash is external to the hole, there's some other considerations as well. Okay, the equations describing incompressible fluid flow through holes apply. I'm talking about liquid, right? Incompressible flow apply. It is this equation here. Okay, considering what? Considering I have some considerations here. If the fluid path length is greater than 10 centimeter, so I'm considering some equilibrium flashing conditions, which means I'm also talking about the flow is maximum. The flow is maximum. And because the flow is maximum, I can assume that the choke pressure equal to the saturation vapor pressure of the flashing liquid. And this is why I can get this equation here. What concerns you for calculations is this equation here if we have a flashing. Okay? What about the last part of our chapter here about liquid pool evaporation or boiling? If you have a liquid pool, so it's like a swimming pool, I don't know how to do a swimming pool, okay, but don't jump in the swimming pool, be careful. Why? Because it's a liquid pool which could be toxic. We're not talking about water. Okay, so now if you have this big pool here, right, we have this big pool inside here. Okay, you have this big pool. I don't know how to draw that big pool. Okay, so it looks like a cake. I'm a bit hungry now. I didn't have lunch. So if you are going to jump into this pool, what do we have? We have boiling, okay? Something is boiling out from this pool. Because of what? Because of the sun, okay? Because of radiation. It could be because of conduction from the earth itself. It could be because of convection. I don't know what came into contact from air. Air is very good. It could be hot air, right? Hot air causing the convection term, causing this to boil, and we have QM. So what is the equation? Our popular equation is the QM here. That comes from evaporation. And we already know that. So it could come from conduction, convection, hot air, or come from radiation from the sun. And this can be calculated by this QG term, where we have the heat transfer coefficient that we are trying to calculate to get the heat flux. And the heat flux is equal to this term here. We are not going to go into the depth of it, but if you want an equation for this, this is the equation for the rate of boiling. Okay, so this is the rate of boiling to calculate how much will be boiling. And I know that we did not go to this into details, but just consider that this will be given, Ks will be given, T will be given, and this is the thermal diffusivity. So you will know this. I mean, all of it will be given. And the time after spill, okay, the time after spill, how much it was there sitting open to the atmosphere, okay? So then you can calculate the rate of boiling. Great. Now this was very good when we applied this equation for LNG, liquefied natural gas. However, for higher hydrocarbons, it requires a more detailed heat transfer mechanism. So there are things that these equations will not be applicable. The final thing I want to mention in this chapter is that there are case scenarios which we call them like the worst case scenarios. And in this case scenarios where we have assuming an entire storage vessel, for example, fails catastrophically. And in this case, what you're trying to show, you're going to trying to show you with worst case scenarios. For example, so if you could have a rupture of the largest diameter process pipe as follows. For diameter smaller than 2 inch, any bore rupture, assume a full bore rupture. Okay, so if you have that small opening for a small pipe, consider it as a full rupture of that pipe. However, it's between 2 to 4 inches. Assume rupture equals to that of a 2-inch diameter. Again, full. For diameters greater than 4 inch, assume rupture equal to 20% of the cross-sectional area. So if there's any rupture, we would say it's about 20% of that cross-sectional area. That hole, you're going to consider it as 20% of that area, okay? If we were talking about hose, the hole is like the whole hose, full. Okay, so this is assuming that based on the worst scenario, and these are the guidelines that would help us into that regards. Pressure relief devices use calculated total release at set pressure. Okay, so what is the pressure? That will be the pressure. I will not consider any drop out in pressure. If I assume a rupture on in a vessel, I'm going to consider the largest diameter that is stick to that, the largest diameter of the pipe that is attached to that vessel. I'm not considering the smaller one. I'm going to consider the biggest one. So this is the way, right? You're considering the things which could go really bad. So for example, the temperature. If you want to consider safety based on a worst case scenario, take the highest maximum temperature. If the maximum highest maximum temperature causes the disaster, and that's the usual case. It's always the maximum, not the minimum. And take the average humidity, and so on. So you're considering here the worst case scenarios based on the guideline that is presented to us. And the last thing I want to mention is that all what we have mentioned is all an indication. There are always uncertainties. There are things that are not, there are uncertainties that mean you're not certain. You're not sure that what we have said is exactly correct. Why? Because you are taking some assumptions. For example, we're talking about the whole size. I do not understand the whole geometry of that size, so I may give a wrong number, which is not that accurate of the diameter or the area of that hole. Or I took some assumptions in the physical properties, or I have a poor understanding of the release of that chemical, that it's a new chemical for me. Okay, and there's a mixture, and I did not understand the mixture, how it will really disperse into the atmosphere. So there are many uncertainties, right? There are many uncertainties, too many unknowns that we have. Uncertainties, too many unknowns. So the consequence that I'm expecting, it could be different. And my modeling procedure is also depending on some assumptions. So what I need to do, I need to always work on the worst case scenario, where I try to mitigate an award and remove the hazard of over designing, putting design into more consideration of safety. So and that will all appear from my modeling study and my dispersion modeling. So my design will depend on all this information. So I should consider a much better design to be more conservative, muhafaz, okay, more conservative of what's going to be happening. So what I need to mention here, the discharge rate, the QM we calculated for either the liquid through a hole or gas through a hole, for a tank or for a pipe, depends on the whole area, depends on the delta P, depends on the Reynolds number, the physical properties, the rho, right, and the temperature of the gas. Also, of course, it will depend. If it's a gas, it depends on temperature. If it's a liquid, it's a different story. That's all what we have taken. I hope that it was a good chapter. It just gives you an idea about QM. And of course, remember, if you know QM and you have an idea of, you will have an idea of CPPM, which is a function of QM and some other parameters, if you can recall the equation, and then you're going to compare it to the threshold limit value. How to find QM? You need the information about the delta P, about the friction, the F, and which you get from KF. We get KF, then you get F. So you need the F term and the delta P. We already have the final equations, okay? You have the final equations. So all what you need is to concentrate more on the final equations that you have. All the best. Wish you all good luck. Thank you very much. Thank you very much. Ma as-salama.